Hello everyone, I'm Rafael, and in this video we are going to talk about TCP versus UDP. But really quick, if you haven't already done so, go ahead and hit that subscribe button below so you can stay up to date on my latest videos. Let's get right into it. TCP stands for the Transmission Control Protocol and UDP stands for User Datagram Protocol. Both TCP and UDP are layer 4 protocols, so they live at the transport layer of the OSI model. Remember, when it comes to the OSI model, we're talking about this layer here. Alright, so with the OSI model, we have our 7 layers. Down at the bottom, we start off with layer 1. That's where our hubs, our cables, our SFPs are going to be. Layer 2, right above it, is where you're going to have your MAC addresses and your switching. So your source MAC address, your destination MAC address inside the Ethernet frame. Then right above that, we have layer 3, which is where routing takes place. And right above layer 3 is where the transport layer is going to be, here at layer 4. And that's where TCP and UDP belong. The purpose of TCP and UDP is really delivery of data. An IP packet has an IP header with a source and destination IP address. That packet gets routed through a network or out on the internet at layer 3. Now, ask yourself, does this data take the same path throughout the network every time? Does it even arrive to its destination in the same order or sequence that it left in? Maybe, maybe not. If there's load balancing involved or network congestion somewhere in the middle, then packets could arrive out of order or not at all. And this could be a problem for a lot of applications. Now, an application on a network needs to decide how to send its data. Should it be reliably or unreliably? That's why we need a transport layer protocol or a layer 4 protocol to help us transport the data. And that's where TCP and UDP come in. Keep in mind there are other transport layer protocols, but the two most popular are going to be TCP and UDP. Let's talk about TCP first. TCP is defined in RFC 793 and it's a reliable, connection-oriented protocol. It has built-in features such as using acknowledgements to make sure data isn't lost in transit. If it is lost, it will resend the data. Here's some data. Cool, I got it. Here's some more data. Cool, I got that one too. Here's some data. Uh-oh, it got lost somewhere. Where's my acknowledgement? Where's my acknowledgement? Oh, let me resend. TCP is also going to make sure that the data was delivered in the same order it left in by using sequence numbers or sequencing. So, traffic is numbered as it leaves. When it arrives, the receiver will look at those sequence numbers and make sure that they are arranged in the correct order before delivering it up to the application. TCP also has flow control to make sure too much data isn't being sent at one time. So, if a sender is sending too much data too fast and the receiver is not able to handle it, the receiver will let the sender know, hey, you're sending me too much data. I need you to slow down a little bit. Now, another great feature is error detection using checksums. So before the data leaves, a checksum value is calculated. That calculation is based on different values inside the TCP header and a pseudo header that has a source and destination IP, which in a way kind of mimics the IPv4 header. So when that calculation is complete, that value will get inserted into the checksum field of the TCP header and the data is sent. When the receiver gets it, it does the same calculation. And if the value it calculates doesn't match the value it received, then the data is considered corrupted. Just a side note, checksums in TCP are mandatory. You must use a checksum to validate that the contents of the segment are not corrupted. With UDP, checksums are optional in IPv4, but mandatory in IPv6. So you can already see that TCP offers a few benefits when it comes to error detection and recovery, but before any of that data is sent over a TCP connection, a reliable connection must be established first by doing something called a three-way handshake. Let's take a look. Alright, so before we talk about the three-way handshake, I want to talk really quick about the TCP header and some of the contents inside. Alright, so right away you're going to notice that we have a source port and a destination port field. And over here on the right we have a list of well-known ports from 0 to 1023 and random ports which range from 1024 all the way to 65535. So in our example below, PC1 wants to communicate with web server 1 over port 80, which is HTTP. PC1 is going to set its source port to something random. Let's just say for an example, 2000. The destination port is going to be port 80. Then we have sequence numbers. Sequence numbers help make sure the data arrived in the correct order. If it didn't, it will get rearranged in the correct order before it gets delivered to the application. Then we have acknowledgements. Remember, the receiver will let the sender know that it got the data. If the sender doesn't get an acknowledgement, it's going to know something happened and the data will get resent. Then you have your header length, you have some reserve fields, and you have flags. Flags are important, and we'll get back to that in a second. Then you have your window size. Window size is used in flow control, and it's basically how much data the sender is willing to accept from its peer before the peer needs to stop and wait for an acknowledgement. Then you have your checksum. Remember, checksums are used in error detection. So before data gets sent from PC1 to web server 1, a checksum value is calculated and inserted into that field. When web server 1 gets the data, it does its own checksum calculation and it compares that value to the one it received. If they match, everything's good. Then you have your urgent pointer, which is used if the urgent flag over here is set. And then lastly, you have options and padding. Okay, so in our example, PC1 wants to communicate to web server 1 using HTTP over port 80, using a TCP connection. So PC1 is going to go ahead and send a SYN message or a synchronized message over to web server 1. And inside the TCP header of that message, the SYN bit or synchronized bit is going to be set. Once web server 1 gets that synchronized message, it's going to send a message of its own back to PC1, and this message is called a SYN ACK or a SYN comma ACK. And inside the TCP header of that message, the synchronized bit is going to be set and the acknowledgement bit is going to be set as well. Once PC1 gets that SYN ACK from web server 1, it's going to send an ACK of its own. Inside the flags of that TCP header, the acknowledgement bit will be set. So what this process means in plain English is that PC1 said to web server 1, hey, I want to talk to you. When web server 1 got that, it said, okay, great. I hear that you want to talk to me, but I also want to talk to you. PC1 said, okay, great. I hear that you also want to talk to me. Let's go ahead and have our conversation. All right, so what I want to talk about next is session multiplexing. Session multiplexing is basically a process where a device or a host is able to support multiple sessions at the same time and manage them individually. Let me show you what I mean. We have PC1 on the left, which wants to talk to server 1 on the right over HTTP, which uses the well-known port number of 80. So when PC1 builds its TCP header, the source port is going to be randomly chosen. So let's just say 62,000. The destination port is going to be well-known port for HTTP, which is port 80. Traffic is going to go out in this direction. Server 1 is going to get it, and when server 1 replies, its source port, these are going to be flipped. The source port for server 1 is going to be port 80, and the destination port is going to be the random port that was on PC1. I highly recommend Googling the well-known port numbers because there's a lot, but I would just focus on the most common ones. So HTTP, HTTPS, Telnet, SSH, FTP, SMTP, things like that, especially if you're going for certifications. So, all right, that's one stream. Now let's say PC1 wants to Telnet to server 1, right? That's a whole nother connection. So the source port is going to be a different port. Let's just say 50,000 because it's a random port. The destination port in this case is going to be 23. 23 is a well-known port number for Telnet. PC1 telnets to server 1. When server 1 replies, the source and destination port are going to be flipped again. So the source port is going to be 23. The destination port is going to be 50,000. And the host is able to keep track of these. And all this is done over one physical link. So PC1 has one NIC, server 1 has one NIC, and there's just one cable. And we're able to maintain all of these virtual connections. And under normal circumstances, when a TCP connection needs to be terminated, a similar process happens, and it works like this. Let's say in our case, web server 1 wants to finish and close the TCP connection to PC1. Web server 1 is going to send a FIN message over to PC1. Now FIN stands for finish. And remember, inside our TCP header, we have our flags field, and here is our list of flags. Now the FIN or finish flag is going to be here. So when this message gets sent from web server 1 over to PC1, the FIN bit is set. And it basically serves as a connection termination request towards the other device. Now, when PC1 gets the FIN, it responds with an ACK acknowledging that FIN was received. So in step 2, PC1 sends an ACK over to web server 1. So that message contains the ACK bit set. Once PC1 acknowledges the initial FIN, it's going to send a FIN message of its own over to web server 1. And in that TCP header, the FIN flag is set. Once web server 1 gets that FIN message, it will send an acknowledgement back over to PC1. Inside that message, in the TCP header on the flags field, the acknowledgement bit is going to be set. And what this basically saying in plain English is step 1 is saying, PC1, I'm ready to close the connection. In step 2, PC1 says, okay, I hear that you're ready to close the connection. By the way, I am also ready to close my connection. Web server 1 says, okay, I hear that you're also ready to close your connection. Let's end it. And as long as there's no more data to be sent, then the connection closes. So this in a way could be a 4-step process or two-way handshakes. and the entire connection is not considered terminated until both sides finish the shutdown by sending a FIN and receiving an ACK back. So we have a three-way handshake to establish a TCP connection, and we have a four-step process or two-way handshakes to end the TCP connection. So if you're downloading a huge file and you want to make sure that everything gets downloaded, and if some of the parts of the download didn't make it, you want them to be resent, and if packets arrive out of order, you want them to be reordered properly. That's TCP. Okay, now it's time for UDP. UDP is defined in RFC 768, and it's a connectionless best effort protocol. There is no three-way handshake to set up a reliable connection. There's also no sequencing like TCP, so data might get to the receiver out of order. There's also no acknowledgements to let the other side know that the message was received, so data isn't even guaranteed. Not only that, but there's no flow control either, so if I'm sending you too much data, too bad. You don't have a way to let me know. So in a way, UDP is sending all this data and saying, all right, I hope you get it. Now, you're probably thinking, with all of those cons, why on earth would anyone want to use UDP? Well, remember the TCP header we looked at earlier? See how it had all these fields and just so much going on? Now look at the UDP header. It's simple, right? That's where the benefits start to come in. Less overhead, and I don't need to wait for a three-way handshake to set up a connection, because with UDP, it's connectionless. That makes it much faster than TCP. And this is great for applications that can actually tolerate packets that get lost or arrive out of order. Some applications that use UDP include video streaming, VoIP, online video games, and other real-time content. If you're on a VoIP call with someone and some packets don't arrive, you don't want TCP to resend them because you might hear the audio again and you're already talking fast in real time. Just repeat what you said and chances are they're gonna hear it fine the next time. Don't resend me old stuff. Just a side note though, VoIP is special. It also uses RTP, which stands for the Real-Time Transport Protocol, and that runs over UDP and offers things similar to TCP like timestamps for synchronization, sequence numbers for packet loss and reordering, and even jitter compensation. UDP is also used for online gaming, so if you're playing Call of Duty and you notice some lag, that's probably because some packets got lost. So you shoot someone once and like 20 bullets come out, and you also did a 180-degree turn. You don't want TCP to resend the packets because then you're probably going to move again and you're definitely going to lose. Just forget the glitch and keep playing, and if you do lose, blame the lag. Okay, so now that we understand TCP and UDP, let's look at the pros and cons of them side by side. So let's start off with reliability. Yes, TCP is reliable, UDP is not. TCP needs to set up a three-way handshake, which is a reliable connection, before we can even send any data. Acknowledgements. TCP uses acknowledgements so that's what the receiver lets the sender know that it got the data. UDP does not offer this. That's another reason why UDP is not reliable. Sequencing. Yes, TCP offers sequencing. When I send data to you, that data is going to have sequence numbers. When you get it, you're able to rearrange the data in the correct order. UDP does not have this. Now, when it comes to speed though, because we have all these checks and acknowledgements and sequence numbers and the three-way handshake that we have to set up, TCP is going to be slower than UDP. Error detection, yes, they both technically have error detection, but there is a difference. With TCP, the receiver will let the sender know that an error has occurred. With UDP, we have the checksums, and if the checksums don't match, then UDP will silently drop the data. It's not going to let anyone know that there was an issue. Error recovery. Yes, TCP has error recovery. If I don't get an acknowledgement or there's something wrong with the data, the receiver will let the sender know so that it can be sent again. UDP does not do this. And with flow control, that's offered by TCP only. Use cases for TCP include web traffic, FTP, and Telnet. Use cases for UDP include video streaming, VoIP, so voice over IP phone calls, and online gaming, and basically any other real-time content, or anything else that isn't a big deal if packets get lost. Alright, so we covered a lot. We talked about TCP and UDP, how they work, what their headers look like, and some examples. Not only that, but we compared both of them side by side. I hope you all enjoyed this video and learned something. If you did, don't forget to subscribe, and I'll see you in the next video. Thanks everyone.